Hello everyone! I reached over 50,000 subscribers! Thank you all so much for doing that. And a special thanks goes out to all my Patreons. I am currently at 4 Patreons, so thank you very much. So please go visit my Patreon account, where you can see some behind the scenes experiments and some Patreon exclusive videos, like my R22 evacuation video. So go check it out, and now let's start the video. So today I'd like to show you the system I made, which stops my solar panel from cooling down the hot tub when there is no heat input from the sun. Okay, so the way it was all set up in the old situation is that the heat from the solar panel was transported by antifreeze through these hoses to this heat exchanger. The antifreeze is just so it won't freeze in the winter. This antifreeze was being circulated by this pump, which was turned on by this timer switch. On the other side of the heat exchanger, the tap water was pumped by this pump through the heat exchanger to carry the heat away from the heat exchanger to the hot tub, and this pump was also turned on by a timer switch. Now the problem with a system like this is that it works fine when the sun is out and heat is being transported to the tub, but when it's cloudy and the antifreeze that circulates through the panel can be colder than the temperature of the hot tub, and therefore the hot tub would cool down. So to prevent this, I needed a system that only circulates water through the panel when the temperature of the panel is higher than the temperature of the tub. So I solved this by letting the pump of the solar panel circuit side be turned on by the timer switch and only start the pump on the hot tub side when the panel circuit is hotter than the tub. The fact that I still use the timer switch for the panel circuit instead of putting a thermometer in the panel and switch it on and off depending on the temperature of the panel is that this way I know the exact temperature that is being circulated through the heat exchanger, and this way the thermal loss through the hoses has been taken into account. So to make a system like this, I needed to be able to compare the two temperatures regardless of the actual temperature of the tub. For example, when the tub is 10 degrees, the panel needs to be thermally connected to the tub when it is between 12 and 15 degrees Celsius, but when the tub is 30 degrees, this would need to happen between 32 or 35 degrees Celsius. So to solve that issue, I used an Arduino and two PT100s. One of the PT100 measures the temperature of the hot tub, and the other one measures the temperature of the panel circuit. The Arduino turns on the pump that circulates the hot tub water through the heat exchanger when the temperature of the panel is 5 degrees higher than the tub, and turns it off when it is 2 degrees higher than the tub. The reason that I'm switching the panel off when the panel circuit is 2 degrees higher than the tub is to compensate for measurement inaccuracies and the heat that is being lost when the tap water is being transported from the heat exchanger to the tub. And the 3 degrees temperature difference creates hysteresis, which prevents the system from switching on and off rapidly when the temperatures are more or less equal. So let me now show you how I've set it up. In this diagram you can see how I've set it up including the LCD, but this is only necessary to calibrate the PT100s. Normally you would use a signal amplifier to increase the output signal of the PT100s, but because I only need an accuracy of around 1 degree, I didn't include that. So as you can see in this experimental setup I made, the Arduino analog input measures the voltage difference between the 1 ohm static resistor and the PT100, which resistance changes depending on the temperature. There's 5 volts over the two resistors, so between the two resistors the voltage is about 2.5 volts. So the changing resistance of the PT100s only generates around 0.1 volts difference or so, which is a very small part of the 5 volt measurement range of the analog input of the Arduino. So this creates a low resolution, and with a signal amplifier a bigger part of that range could be used. You could of course also use a different temperature sensor, but these ones were the only ones I could find that were watertight. Maybe later I will include a signal amplifier so I can display the temperatures accurately, but for now it's okay. In this case I use pin 7 of the Arduino's digital output, which activates a relay to turn the pump on and off. For this demonstration I'm using an LED to show the output signal of pin 7. So to calibrate the PT100, I used this piece of code that I copied from a YouTube video that I can't find anymore, and therefore I unfortunately can't give credit to by name, but still thanks a lot whoever you might be. I never really looked into how the code exactly works, but in any case it divides the temperature difference through the sensor value, which gives the temperature change per value change, and because you need to give below values for the temperature and the sensor, it creates a base from which it starts counting. So to do the calibration, you take a cup of water with ice in it to get the temperature as low as possible and use a separate thermometer that is reasonably accurate, depending on your needs, to measure the water temperature. Then put the PT100 in the water and write down the sensor value and the water temperature. Then do the same thing with hot water and also write down the sensor value and the water temperature. Then calculate the measured temperature difference of the water and enter that difference here, and also input the low temperature here. Then calculate the sensor value difference and write that down here, and also input the low sensor value. Now the Arduino knows how to calculate the temperatures and will display that here. So now we can use those temperatures in this piece of code to determine when output 7 should be high or when it should be low. Now, because I could not figure out how to write this little piece of code, I asked ChatGPT to write it for me, and it did. This saved me a lot of time searching, and now I know how to write something like this. Pretty great. And I've put the Arduino code in the description in case you're interested. So now you can see that when temperature sensor 2 measures a higher temperature, the LED turns off and the other way around. Easy peasy. Okay, so now to the actual setup. This is how I've set it up now in this hot tub filter pit. So this is the Arduino housing, the panel circulation pump, the insulated temperature sensor that measures the panel circuit temperature, a pressure gauge, an automatic air vent, and some valves and couplings to fill the system. A timer switch which powers these 12-volt transformers from 6 in the morning till 6 in the evening. One of these transformers powers the panel circulation pump and the other one powers the Arduino system. And this is the heat exchanger with the hot tub circulation pump and a one-way valve to stop circulation through the heat exchanger in the opposite direction when the filter pump is on. The heat exchanger is connected to the hot tub through these hoses. This is the connection of the other temperature sensor, which goes through the suction tube to the bottom of the hot tub. And you can see here the sensor cable was a little bit on the short side, so I tied it up with a piece of string. Not the prettiest solution, but it gets the job done. And in case you were wondering, this timer switch activates the filter pump of the hot tub, but that's not important for now. So in this housing you can see the Arduino, the two static 100 ohm resistors and the relay module. And this relay module turned out to be a low activated relay, and it took me a while to figure that out, so that was quite an interesting afternoon. And in the end I just had to switch these two output values from high to low and vice versa. So these connectors are temperature sensor 2, temperature sensor 1, the hot tub circulation pump power output and the main power input. So this whole system makes sure that there is no heat lost through the panel system, but now you are probably wondering how well it works, and I can't of course give you an exact number because there are so many variables, but on average it used to cool down about 5 degrees during the day when it was cloudy, and now it's only 1 degree, which is just the natural rate of cooling of the tub through the insulation. Okay, so now a short follow-up on the panel itself. It is working okay, but as you can see the polycarbonate was deformed a lot and even is loose at the bottom, and that is because about a year ago the circulation pump stopped working on a very hot day, so then the temperature inside the panel rose to at least 135 degrees Celsius, which is the glass temperature of the polycarbonate, which means that it was no longer a solid and started melting. As you can see, it deformed nicely around the contours of the panel inside, and you can even see an imprint of a screw head here. For now all of this is okay, but in time I have to replace this sheet, and I'm thinking about using glass with an infrared reflective coating to increase efficiency. And I'm also thinking about painting the collector with one of those blackest black paints to see if that improves it even more, but that's something for later. Okay, that's it for now. Please check out my Patreon account for all those nice extras. Thank you all so much for watching and see you next time.